All right, last time we met, I introduced the chapter on gases, chapter 13, which will be covered in exam 7. And today is listed in your syllabus as a buffer day. And that's there in case I run out of time introducing the topic. But since I finished last time we met, I'm going to use the buffer day for review. And then that's this Tuesday of this week. Thursday, we'll meet again. But if I have finished the review for today, Thursday, I'll just show up for the first part of the class to see if anybody Zooms in or comes in person and has problems that we need to deal with. Otherwise, after about 30 minutes, I'll shut the class down. So let's get into our review. And this is based upon the review document that's that I hand out in person or is available on Brightspace in the module for chapter 7. And I've highlighted some that I want to be sure and get to. All right. So number 1 for in chapter 13. There are 2 balloons. Both have the same size and temperature. Okay, so sometimes drawing a picture really helps. You have 2 balloons, roughly the same size. So that means the volume of 1 equals the volume of 2. And the temperatures are the same. So the temperature of 1 equals the temperature of 2. All right. 1 balloon contains hydrogen. So let's just arbitrarily, we'll say this one has hydrogen gas in it. And the other balloon has carbon dioxide. All right. The hydrogen balloon floats and the carbon dioxide balloon sinks in air. Which balloon contains a greater number of molecules? All right. This is perfectly illustrates the dangers, the cautions of word problems. Word problems, I've said before, and I'll say it again, word problems are designed to confuse. They will confuse anyone who doesn't understand the material. So there's a lot of information in here, which might be valuable for a different problem, but not for this one. Except to say that they're the same temperature, the same size, and we have to assume they're the same pressure because they're both in the atmosphere, right? We have the same pressure on each one. So this is referencing Avogadro's law. Avogadro says it doesn't matter what the gases are. If the question is, how many molecules are there? And which one has the greater number? Neither. The number of moles of hydrogen equals the number of moles of carbon dioxide. That's Avogadro's law. Now, the fact that hydrogen floats and carbon dioxide sinks has to do with density, right? So the mass of hydrogen for this volume is much less than the mass of this one and that volume. So that this one floats in air because its density is less than air. This one sinks in air because its density is greater than air, right? Density, remember, density equals mass per unit volume. The volume is the same for both of them. So the masses must be different. And if they have the same number of particles in each one, the mass, compare the mass, this mass is 2.02 grams per mole. And this one is 12 plus 32, which is 44.01 grams per mole, right? Carbon dioxide is 20 times the mass of hydrogen, right? So its density is going to be much greater And if the density is less than the density of the fluid, right, the air, then it will sink. Excuse me, if it's greater than, it'll sink. If it's less than, it'll float. All right, so the answer to this question is A, both balloons contain the same number of molecules. And I know I took a long time to describe this situation and give you the answer, but I think it's a lesson well learned. This is referencing Avogadro's law. All right, so let's move on to number 2. Number 2 says, you place 15 grams of nitrogen gas and 15 grams of hydrogen gas in a container fitted with a massless, frictionless piston. All right, so we have a container here. We have a piston in it. And inside that container, we have 15 grams of nitrogen gas and 15 grams of hydrogen gas. Okay. If the original volume of the container is 11.4 liters, so the volume, initial volume equals 11.4 liters. What's the volume after the reaction has run to completion? And the temperature is constant. Temperature is constant. Okay, so we have to assume that the pressure is also constant because this piston can move. So we have a constant pressure also. All right, so you're given the reaction equation there, which is the Haber process. And here we go. Now, what are we saying? Well, what we're saying is that we start off with 4 moles on this side, end up with 2 moles on that side. But the problem is, this is grams. We don't know the moles yet. So the moles of nitrogen would be, let's do it over here. 15 grams of nitrogen. And we got to convert that to moles, right? Molar mass, grams per mole. So nitrogen, dinitrogen would be 2 times 14.01, which would be 28.02. All right, so how many moles? Need my calculator. Let's see, 15, enter 28.02, divide. So this is 0.5353. I can do better than that. Moles of nitrogen. How many moles of hydrogen do you have? Well, we have 15 grams of hydrogen, and the molar mass of hydrogen is 2.02 grams per mole. So 15 enter 2.02 is 7.426 moles of nitrogen. Excuse me, hydrogen. Okay, this is a problem where you've got absolute amounts of both reactants. So one of them is going to be limiting. We've calculated that we have 0.5353 moles of nitrogen, and we have 7.426 moles of hydrogen. Okay, so which one is limiting? Well, we could take this one and say, convert all of that one to ammonia. And then take this one, convert all of that one to ammonia. But we really don't have to do that because we know that for every one of these, you need 3 of those. Right? So that's, let's see, let me use my calculator. This is 1.606 moles of hydrogen are required. Okay. All right. So on this side of the equation, we have a total number of moles. How many? We have 0.5353 plus 7426. 0.5353 plus 7.426. Okay, 7.961 moles on this side of the equation. How many moles do we have on that side of the equation? Remember, we're looking for the final volume. And if we know Avogadro's law, we also know that the initial volume divided by the initial moles equals the final volume divided by the final number of moles. Oops. Right? So if we know the initial volume, which is 11.4, and we know the initial number of moles, which is 7.961, then all we need to know is how many moles are in the product, or how many moles are left over after the reaction. Total moles. Then we can calculate volume. Right? We've got the initial moles. Now we need how much of this is produced. Well, we know that this is how much hydrogen is used. And this is how much is produced. Right? We have ammonia, 2, 1 nitrogen, and that equals 5353, which is 107.1 moles of ammonia. Okay. So that means we have this much. We have this much to begin with. On this side, we have that much ammonia. How much nitrogen do we have? We have 0 moles of nitrogen because it was all used up. How much hydrogen is left over? Well, we used up that much out of this much. So 7.426 minus 1.606 equals 0 to 8, and 1.6 is 5. This is 5.820 moles of hydrogen left in that container. So this is the total moles, final moles. All right, so that's 1986. That's after, and this is before. Or this would be what we would call in initial, and this would be in final. Now we can determine the volume. Right? We just need to solve for the final volume. So the final volume is equal to VI over NI times NF. Okay? So the final volume is going to be the initial volume, which is 11.4 liters. The initial moles is 7.961. And then the final moles is right here, 6.891. All right, that's the hard part. Now we're just going to crunch some more numbers. And that's 10.2 liters. Well, how did we get 9.87 out of that? Hold everything. Ah, no, that one's right. All right, I must have made a calculation error here. Everything's right down to here. So let me try that calculation one more time. 11.4. Right. 6.89. 1. And then 7.961. Ah, I did make a mistake. This should be 9.3 significant figures. 8, 7 liters. There we go. That's C. Calculation error. So that one took some work. It was all based upon Avogadro's law. Okay. Oop. Pause for a moment. All right, number 7. You're holding 4 balloons, each contains 6 grams of different gas. The balloon containing which gas is the largest? All right. So we got 4 balloons. And they're different sizes. So I don't need to make them the same size. And we've got different gases. Let's see, we've got nitrogen to choose from, helium, krypton, and neon. All right. And the sizes are not relative yet. But we have 6 grams of each. 6 grams. All right. Which one is the largest? All right, so what we're saying is the one that's the largest is the one that has the greatest number of molecules or atoms, as the case may be, right? That's an atom, that's an atom, that's an atom. This is a molecule. So which one has the greatest number of particles? Well, if they have the same mass, then it takes fewer particles of the heavier atom or molecule to make the same number of particles. Right? So they're going to have different numbers of particles because they have the same masses. So the one that has the heaviest atom or the heaviest molecule will have the fewest number of particles and will be the smallest balloon. So which one's the heaviest? Well, let's see. Let's look at their molar masses. That's the way to compare them. Nitrogen is going to be 28, right, grams per mole. Helium is about 4. Krypton is 83.7. Actually, 84, rounded off. 84. And neon is 20 grams per mole. Okay. So the smallest number of particles, if they're the same mass, it takes fewer krypton atoms to make 6 grams than it does for neon to make 6 grams. It takes more of them because each one weighs less. So the one that has the greatest number of particles will be that atom or molecule with the smallest molar mass. That would be helium. That's the greatest number of particles in each one of these. All right, number 8. Hydrogen peroxide decomposes to form water and oxygen according to the following equation. Okay, so we have 2 hydrogen peroxide in aqueous solution. It decomposes to form water and oxygen. That's why it fizzes, because of that one right there. Okay, suppose 145.9 grams of hydrogen peroxide, 145.9 grams of hydrogen peroxide decomposes and all the oxygen gas is collected in the balloon. So all this oxygen gas, which we don't know how much yet, but is collected in a balloon, right? And the balloon is at 1 atmosphere pressure and 25 degrees Celsius. What's the volume of the balloon? All right, how do we get there? Well, this part of the problem is a state function. In other words, we learned our gas laws, right? Some of them we can do before and after, but in this case, we only have the current state, the current situation. That means we have to use the ideal gas equation. All right. So we know temperature, and all we have to do is add 273 to equal K. Let's go ahead and do that. That's 298 K. 1 atmosphere pressure. Volume will be our unknown. What we need is moles. We have to get moles from here. Moles of oxygen. Okay. So how do we get moles of oxygen? Well, we've got grams of hydrogen peroxide, but remember, in a balanced equation, you can't move anywhere with mass. You got to have moles to move. So to go from here to here, we have to convert that to moles. So what's the molar mass of H2O2? Right? 2 hydrogens and 2 oxygens. right? So that's 3234.02 grams per mole. All right, so we're going to convert this using molar mass. That'll tell us how many moles of hydrogen peroxide we have. Which is 4.289 moles of H2O2. Now we got to convert to moles of oxygen. And we need a conversion factor that will do this number, right? Cancel these, leave us with that. That's the coefficient, 1 and 2. So divide 2 into that. And we get 2.144 moles of oxygen. Now we have everything we need. We just have to solve this one for volume. Right? So the number of moles of oxygen is 2.144 moles. And R, right? R will be in useful information, either at the end of the paper exam, or it'll be a separate document in Brightspace that you need to make a copy of before you take the exam. So that's 0.08206 liter atmospheres per mole K. And then 298 for the temperature. Right. Then we divide by pressure, which is 1 atmosphere. Okay. So that's the hard part. Now we're just going to crunch some numbers. Let's see, I've already got that one in there, 0.08206 times and 298 times divided by 1 is 52.4 liters. Okay, and that's C in your multiple choice. All right, number 8. Let's see, who's next? Moving on time. Number 11. A gas is collected over water at certain temperature. The total pressure is 758 torr. The vapor pressure of water at the temperature is 17 torr. The partial pressure of the gas collected is what? It's simple. This is very simple. This is Dalton's law of partial pressures. Remember, total pressure, in this case, is equal to pressure of the gas plus the pressure of the water vapor. Okay? So we know the total pressure is 758 torr. The pressure of the gas is unknown. But the pressure of the water is 17 torr. Right? So the pressure of the gas is simply 758 minus 17. Which is 741 torr. Is that one of our selections? That would be D. Okay. Let's see, let's scroll down to number 18. A flexible weather balloon contains helium gas at a volume of 855 liters. Initially, the balloon is at sea level, where the temperature is 25 degrees and the barometric pressure is 0.947 atmospheres. The balloon then rises to an altitude of 5,500 feet, where the pressure is 0.785 atmospheres and the temperature is 15 degrees. What's the change in volume of the balloon as it ascends from sea level to 5,500 feet? Okay. This is a problem where you have before conditions and you have after conditions. So, but several of those variables are changing, right? Pressure is changing, temperature is changing, and volume is going to change, those three. So we need the combined gas law. Remember that one? P1 V1 over N1 T1 equals P2 V2 over N2 T2. Okay. Now, are there any of these factors that remain constant? Yes. Moles of gas. The helium gas is trapped in that balloon, and that does not change. So we don't need this factor. Right? So there's your equation. All right. So let's change it to this. Initial conditions and final conditions. There we go. Now let's set up a table. Initial pressure, initial volume, initial temperature, final pressure, final volume, and final temperature. And let's put these values in here. Extract them from the problem so we don't get the wrong ones placed in the wrong place in our equation. Okay, so we're starting off at a gas volume of 855 liters. Initial volume, 855 liters. At what pressure? 0.947 atmospheres. And at what temperature? 25 degrees. That's Celsius, right? Remember, we always have to change to Kelvin. Then what's the pressure at 5,500 feet? 0.785 atmospheres. What's the final volume? We don't know. That's the unknown. And what's the final temperature? 15 degrees? 15 degrees Celsius plus 273 equals 8H2. All right. Now we can solve this for our unknown. Final volume. Right? So it's going to be initial pressure, initial volume, final temperature. And then initial temperature, final pressure. 1, 2, 3, 4, 5. 1, 2, so 1, 2, 3, 4, 5. Okay. So now we just substitute the numbers. We've got them over here. We just put them in the right place. 0.947. I'm going to leave the units out just to save space. 855 liters. Final temperature, 288 K. Initial temperature, 298 K. And final pressure, 0.785 atmospheres. All right, so now we just need to crunch the numbers. Times 855 times 288 divided by 298 divided by 0.785 And that is 997 liters, 997. Oh, scientific notation, right? 9.97 times 10 squared liters. That would be, oh, excuse me. This is the final volume. This is not the change in volume. The change in volume equals the final volume minus the initial volume, which would be 997 minus 855, which would be 1.42 times 10 squared liters. That's how much the volume changed. Okay. Right, that was number 18. Next, 21. Consider the following unbalanced equation. All right. C2H5OH. C2H5OH. And this is a gas plus oxygen yields carbon dioxide and water. Yep. Okay. That's an unbalanced equation. This is ethanol. This is the drinking kind of alcohol. And we're going to burn it. This is a combustion reaction. And complete combustion of any carbohydrate, in this case, will always produce carbon dioxide and water. Okay, what are the other conditions? We have 1.55 grams of this ethanol. All right. And we're reacting with 10 grams of oxygen. Okay. What's the total volume of gas present in liters after the reaction is complete, assuming the reaction takes place at 1 atmosphere and 25 degrees? Okay. In order to answer the question, we have to know how many moles of gas are remaining. And the first thing we have to do is balance the equation, right? This equation is not balanced. So let's use our budget just to be safe. We have carbon, hydrogen, and oxygen. So on this side, we have 2 carbons, we have 6 hydrogens, and we have 3 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay. Let's start with carbon. We're going to leave oxygen till last, remember? So if we want 2 carbons, 2 there, that makes 2 carbons. It also makes 4 plus 1 is 5. 5 oxygens. Okay. So now hydrogens. We need 6 hydrogens on this side. So if we put a 3 here, that will give us 6 hydrogens. It'll also give us 3 plus 4 is 7 oxygens. Now, how do we get 7 oxygens out of 2 plus 1? Right? Well, this is 6 plus 1, correct? 7. We've already got 1. We need 6 here. So if we put a 3 there, that gives 6 plus 1 is 7. There we go. So now our equation is balanced. Now we can do the stoichiometry. All right, what we have to do is find out how many moles of ethanol and how many moles of oxygen do we start with, and then find out which one is limiting. So we need a molar mass for ethanol. So that's 2 times 12.01 and 6 times 1.01 for the hydrogens, and then 1 oxygen. Okay, so let's find out what the molar mass is. Let's see, 24.02 for the carbons, 6.06 for hydrogens, and 16 for the oxygen. That's 46.008 grams per mole. So we can take this 155 and convert it to moles. Okay. 46.08, and that's equal to, let's see, 3.364 times 10 to the minus 2 moles of ethanol. That's my abbreviation for ethanol. How many moles of oxygen do we have? Right. 2 times 16 is 32. Okay. So we need 10 divided by 32, which is 3.125 times 10 to the minus 1 moles of oxygen. Okay. Okay, so we need to calculate, we need to find out which one is limiting. We know how many moles of these gases we start with, and this is the starting number of moles. We need to find out how many moles of product we have. Okay, so let's look at it this way. If we have this many moles of ethanol, how many moles of oxygen are required? Because we have this many moles of oxygen, right? So this will be ethanol and oxygen. So we have 1 here and 3 there. So 3 times, let's see, let me swap those. 3 times that is 1.009 times 10 to the minus 1. Okay, this is how many moles of oxygen are used. Okay, so we know, since this is a smaller value than that one, that this is limiting. And this is excess. Okay? All right. Now that we know that this is the limiting one, we can take this many moles of ethanol and find out how many moles of carbon dioxide and how many moles of water. So how many moles of carbon dioxide are produced? We have 3.364 times 10 to the minus 2 moles of ethanol. Now we're going to find out how many moles of CO2 are produced. There's 2 there and 1 there. And so 3.364 2 times, we have 6.728 times 10 to the minus 2 moles of carbon dioxide produced. Okay? So we can either take this one and go to water, or we can take this one and go to water. Let's go ahead and use this one. Okay. Same value here, different conversion factor. 1 ethanol, now it's 3 waters. This is 1.009 times 10 to the minus 1 moles of water. Okay. So out of all this jumble of numbers, what we need to know is the moles, the initial number of moles equals what? The initial number of moles is the total amount of ethanol, which is this. 3.364 times 10 to the minus 2 moles of ethanol. And how many moles of oxygen were there? Right, 3.125 times 10 to the minus 1 moles of oxygen. Right? So that's the total, the initial moles of gas. Right? Hold on a second. You know what? No, I'm approaching this the wrong way. I'm approaching this as before and after. Actually, what I need is to know the total number of moles of gas at the end. So let's look at this a different way. How many moles of ethanol are left over? 0. It's limiting. Right? So all of those are gone. Now what do we have left over? Well, we started off with this much oxygen. How much oxygen did we use? Right here. So subtract 1.009 times 10 to the minus 1, and that's how much oxygen is left over. .116 moles of oxygen remain. Yeah. So we got this oxygen remaining. We got this carbon dioxide produced, and this water produced. So the total number of moles equals that one plus this one plus this one. Let's see. 6, 8. And I get 3.798 times 10 to the minus 1 moles of gas. Okay, so that's the total number of moles of gas. We're looking at this equation. Okay, and the question is, what is the total volume afterwards? There we go. We got the moles, we got the constant. What's the temperature? Temperature equals 25 plus 273 equals 298 K. Right, so we got the total number of moles. Let's say 0.3798, 0.3798. R is 0.08206, 298 K divided by, what's the pressure? Pressure is 1 atmosphere. Now we can calculate the volume. Let's see, 0.08206 and 298 is 9.29 liters. Let's see. Where did I go wrong? Total volume of gas present after the reaction is complete. All right. I think I made a calculation error somewhere. Let's see, moles of ethanol, 3364, yes. Moles of oxygen, 0.3125, yes. 0.06727 carbon dioxide, yes. And oxygen, 0.1 consumed. Yes. So we have left over that much. Okay, that's good. Carbon dioxide, oxygen. Oh. This mistake was made at the very beginning. At 25 degrees Celsius, water is a liquid. So we don't need this one. All right. So what I have to do is 3.798 and subtract 1.009. So the total is not this one. The total is 0.2789 moles. Okay. There we go. So now the calculation should give us 6.82 liters. Details will kill you every time. All right, moving on. Notice how the multiple choice selections incorporated that exact error that I made. Because the answer I got the first time was 9.29, I would have put down C. But correcting the mistake, the answer is actually A. All right, 23. You're playing with a helium balloon on a typically warm California day. And let's say I'd rather play on Georgia. Typically warm Georgia day. Suddenly the Celsius temperature doubles. Which of the following is true? All right, so volume, pressure, and temperature. We're looking at those three. So initial, final, final, and final. Okay. The actual temperature needed to answer this question. Not necessarily. If we say that the Celsius temperature initial, right? The Celsius temperature initial doubles. Right? So now the final temperature in Celsius is equal to twice that value. Correct? Right. The final temperature is twice what the original temperature was in Celsius degrees. So let's set A aside for the moment. What happens to the volume? Well, if we take Charles' law, right? If we say that the pressure inside the balloon is going to be 1 atmosphere no matter what you do, because the pressure outside the balloon is 1 atmosphere. So the pressure question is irrelevant. What we have to focus on is the volume. So let's take pressure out of the equation and look at Charles' law only. Okay, now what happens to the temperature? If this temperature doubles, we know that this temperature must be in K. Right? So what happens to the K temperature? Well, this temperature is going to be T degrees C F plus 273. And this one's going to be 2 times T degrees C initial plus 273. So what happened to the Kelvin temperature? Well, the Kelvin temperature did not double because we've added 273 to both sides. We can't say that the temperature actually doubled. The temperature went up, so that means the final volume will increase slightly. But the volume of the balloon will not decrease. It will increase, but the volume will not double because we did not double the Kelvin temperature. So the volume of the balloon will slightly increase. That's your best answer. Right there. Simply because the doubling did not happen to Kelvin. It happened to degrees Celsius. All right, 24. Which of the following statements is true of 19 grams of fluorine gas at STP? We have 19 grams of fluorine gas at standard temperature and pressure, right? So the temperature is going to be 0 degrees C, right? That's standard temperature for gases. Pressure is 1 atmosphere. All right. Now, which one of these is true? Well, let's see. How many moles is that? 19 grams of fluorine? That's half a mole, right? Because 19 grams is the molar mass of 1 fluorine. And 38 grams per mole is that one. So this is going to be 0.5 moles of fluorine gas. Right, we know that. All right. A, it contains the same number of molecules as 1/2 mole of O2. Yeah. Right? If it's got the same number of moles, it's got the same number of molecules. So A is true. Right? A, that's true. Well, the only other oddball we have in there is none of the above. Right? And we found one that's true. So we can stop there if we want. It exists only in the form of ions? Well, no, right? It's molecular. It occupies a volume of 22.4 liters. All right. What would it have to be to occupy 22.4 liters? It would have to be 1 mole. That's the molar volume of gas at standard temperature and pressure. So it would actually occupy 11.2 liters, half that volume. It contains 6.02 times 10 to the 23rd molecules. No, it contains half that much. 3.01 times 10 to the 23rd. All right. So the only answer that fits is A. That is true. And next highlighted one, 28. Okay. A compressed gas cylinder at 137 atmospheres and 23 degrees C is in a room where a fire occurs. Fire raises the temperature of the gas to 475 degrees C. What's the new pressure in the cylinder? Right. This is a before and after. And we're relating pressure and temperature. How do we relate pressure and temperature? Right? There's no law that related the pressure and temperature directly, but we have a combined law, PV over T and PF over TF. So is any part of that constant? Well, I left out moles. Right? Moles doesn't change. The cylinder is sealed, right? So moles is the same. Temperature changes, yes. Pressure changes, yes. How about volume? No, not unless the gas cylinder flexes. So we have to assume the volume stays the same, right? Volume stays the same, volume stays the same. So there's your relationship. So initial, final. What's the initial pressure? 137 atmospheres. What's the initial temperature? 23 degrees. Plus 273 equals 296 K. Okay. What's the final pressure? We don't know. That's the unknown. And 475 degrees C plus 273 is the final temperature. So that's 8, 4, 7. Okay. Now we can solve the problem. Solve for final pressure. There we go. So now we can put our values in there. 137, final temperature, and initial temperature. And then we can calculate the final pressure in that cylinder. And I get 346 atmospheres. So the pressure, about 2.6 times as much. 346 atmospheres. Oh, scientific notation. 3.46 times 10 squared atmospheres. There you go. So that's C. Now, I don't know if that cylinder can hold up against those pressures. Maybe, maybe not. We're not given that information. But just to be safe, if there's a fire around compressed cylinders, evacuate. Not the cylinder, you. Leave the area. And call 911. Okay. All right, 29. Which of the following statements is true about the kinetic molecular theory? All right. Remember, the kinetic molecular theory of gases says that gases are composed of very small particles that have lots of space between them. Right? So the volume of the particle is insignificant. It's the volume between them that matters for the volume of the gas. But those particles do have mass, they have kinetic energy, and when they smack into each other, they bounce off as if nothing happened. They're just like billiard balls. There's no interaction between them. There's lots of them, huge numbers. And they're in constant rapid motion, right? And they impact the walls of the container, and that's how we can sense pressure. All right, how about these? Which one of the statements is true? Pressure is due to the collision of the gas particles with the walls of the container. I just said that. That is true. A is true. B, gas particles repel each other but do not attract. That's false. According to the theory, they don't do either. They're just like billiard balls when they bounce off each other. At least two of the statements are correct. Well, we found one. A is correct. A is true. How about D? The volume of the gas particles is considered to be small. About 0.1 milliliters. Okay. We would have been safe by saying small, but now when you put 0.1 milliliters in there, that's not an insignificant volume. So D is false. The volume of the gas particle is much, much, much smaller. It's almost vanishingly small compared to the volume of the gas. So D cannot be true. E, adding an ideal gas to a closed container will cause an increase in temperature. The kinetic molecular theory of gases says nothing about that scenario. When you add a gas to a closed cylinder, it doesn't say that the container will increase in temperature. In fact, it says that the average kinetic energy of all the particles in the container is proportional to the temperature. So if you add a gas, we can't even tell because you don't know what the temperature of the gas is that you're adding. So E cannot be true because first of all, it runs counter to one of the postulates of the kinetic molecular theory, and we're not told if there is any difference in temperature of the gas that you're adding. So we can't keep E is false for a couple of reasons. So A is the only true one in that group. The last one, E, is kind of tricky. All right, 30. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. Okay, let's see. Are we going to need this equation? Magnesium metal plus hydrochloric acid, which means it has to be aqueous, yields magnesium chloride in solution plus hydrogen gas. And here we go. How many liters of hydrogen gas are produced? We're going to have to balance the equation. I think we can do this one without the budget. We need two hydrogens. So that's two hydrogens, two chlorines, one magnesium. It's balanced. Okay. So what are the initial conditions? 3.02 moles of magnesium. Okay. And 3.02 moles of, moles of hydrogen chloride or hydrochloric acid. How many liters of hydrogen gas are produced? At 1 atmosphere and 49 degrees, P equals 1 atmosphere. Temperature equals 49 plus 273. Right, so that's 2, 2, 3. Okay. All right. How many liters? We're going to need to know moles. in order to determine liters. All right, so how many mole? Which one is limiting? 1 mole of magnesium requires 2 moles of hydrogen chloride. So 3.02 moles was going to require 6 moles of HCl. So this is limiting. Right? We're going to run out. And we'll still have some solid left over. So this is going to be gone. And how many moles of hydrogen gas will it produce? Right? So we're going to convert like that. We have 1 here, 2 there, and it produces half. Let's see, 1.51 moles of H2 gas. Okay. Now we have our value here, 1.51 moles. Now we can solve the ideal gas equation for volume. 1.51 moles, 0.08206 for the constant. Temperature is 322, and pressure is 1 atmosphere. So 1.51, 0.08206, and 322, and that's 39.9 liters. That would be D. Okay, scroll. Got about a half hour left. Let's see what we can get done in that half hour. 34. If temperature and pressure are held constant, the volume and number of moles of gas are. Okay, remember the relationships: pressure, volume, moles, temperature. If we hold 2 of them constant, then we have a gas law that will describe the other 2, probably. Temperature and pressure are held constant, right? Constant. Temperature and pressure, constant. Volume and moles. This is Avogadro's law. And it says initial volume over initial moles equals final volume over final moles. Okay. So the volume and number of moles of gas are directly proportional, inversely proportional. They're not independent. They're related. They're not equal. How are they proportional? Well, the relationship here actually is this equals a constant value. So remember, whenever you have a quotient equal to a constant, the relationship of the variables is direct. As this one goes up, that one goes up. Or as this one goes up, that one goes up, in order to maintain constant. Right? If this one gets bigger, that one has to get bigger. Otherwise, you don't have a constant anymore. So this is a direct proportion, D. Okay. 37. Perform the following conversion of pressure units. Okay. I'm not sure why that 1.177 is sticking out there to the right. Typographical error. So we want to go from atmospheres to torr. We're given 1.177 atmospheres. We want to end up with torr. So what's the conversion factor? Right? Atmosphere is in the denominator, torr in the numerator. 1 atmosphere is 760 torr. So 760 times 1.177, which would be about, 840, 850, something like that. 894. Yeah, 894.5. That was easy. Let's see, another one. Here we go. 43. A sample of argon gas occupies a certain volume at 15 degrees. So we've got argon gas. We know. We have a volume equal to something. And we know that the temperature is 15 degrees. See. Okay. At what temperature would the volume of the gas be 3 times as big? All right. So here's the way I'm going to solve this. This has to be 273 equals, let's see, 288K. And if we know before and after, right, volume and temperature, that's Charles' law. So initial volume, initial temperature, final volume, final temperature. Right? The initial volume is some value. The final volume would be 3 times that value. This would be 3x. The initial temperature is 288K. Okay, we want to know what is this one. All right, so the relationship here is VI over TI equals VF over TF. And we want to know TF. So bring TF over here, bring VI over there, and TI over here. F, TI, and then VI. Yeah. Okay, now let's substitute what we know. VF is 3x. TI is 288. Okay, and VI is x. So the x's cancel, and 3 times 288 would be the temperature. $864K. But our temperatures are in Celsius, the choices that we have. So we have to change it to Celsius. 273 subtracted from that. And that's 591 degrees C. Which would be answer C. Okay? $43, $49. Let me see how many more we got to go. One, two, three, four. I think we're going to be able to finish today. Which of the following will give a graph with a straight line and a y-intercept of 0? All right. We've got volume and temperature. Right? Volume and temperature. Right? Remember, during the lecture, if this is temperature in degrees C, and this is volume in whatever, we'll say liters, okay, then what we find is a straight line like that. And if we extend that line, it goes like that. So all plots of volume and temperature are going to be straight lines. But y-intercept of 0, right? A y-intercept of 0 would have to be down here. So where would that be the case? Well, that would be the case not where the temperature was degrees C, but where the temperature was K. Then we have like this. Well, actually, we don't need to draw a separate line. If now we change this to K, the intercept here is at the origin. So in other words, the temperature must be K and the volume can be anything. All right, so the volume versus temperature in K will give you a straight line with a y-intercept of 0. And that would be C. Right, 4952. Solid carbon dioxide is placed in a Ziploc bag, okay? At a certain temperature, solid carbon dioxide sublimes, turns directly from a solid to a gas at a rate of 0.726 grams per minute. How many gaseous carbon dioxide molecules are present after 4.84 minutes? All right. Oh, there's a lot of blue smoke in here, or a lot of condensation from the sublimating carbon dioxide. All we need to know here is how fast does it sublime and how long are we given? That will produce 0.726 grams per minute, right? And how long is it going? 4.84 minutes. Right? We could do this all in one calculation, but I'm going to split it up so it'll make more sense. Right? The minutes cancel and leave us with grams, and we have 3.514 grams of carbon dioxide. Okay. The question is, how many gaseous carbon dioxide molecules are there? So what we have to do next is convert this to moles. Right? So what's the molar mass of carbon dioxide? 12.01 for carbon and 32 for oxygen, right? 2 oxygens. We got 4401. That'll give us moles. But we're asked for the number of molecules. So now we need to convert moles to molecules, which is 6.022 times 10 to the 23rd. Okay. So now we can take this number, divide it by 44.01, and multiply it by 6.022 10 to the 23rd. And that gives us 3 significant figures. 4.81 times 10 to the 22nd molecules. That would be C. Right? And 55. The air in the inner tube of a tire of a racing bike has a pressure of 116.8 pounds per square inch. Convert that to atmospheres. All right. So useful information will have the conversion factor. We're converting from 116.8 PSI, pounds per square inch, to atmospheres. So how many PSI is one atmosphere? 14.69. 116.8, yes. 14.69 divide, and I get 4 significant figures. 7.951 atmospheres. 7.946. Here's the difference. That calculation probably used 14.7, which would give you a slightly smaller number here. Right. So test taking technique, if you have all unique answers to choose from, pick the best one. And the best one in this case is C. All right, 55. 60. You're holding two balloons of the same volume. All right. Two balloons. And volume 1 equals volume 2. Right? So far, that's all we're given. One balloon contains 1.05 grams of helium. 1.05 grams of helium. The other balloon contains neon. All right. What is the mass of the neon in the balloon? All right. Here we have to make some assumptions. We have to assume that the temperature of each is the same, and the pressure, of course, will be the same. That means the number of moles equals the same. The number of moles of helium equals the number of moles of neon. Okay? So if the number of moles of neon equals the number of moles of helium, the difference in the masses is the relationship of the molar mass of each. So helium is about 4, neon's about 20, roughly. So that's an increase of 5 times. Right? So the mass of this one is going to be 5 times the mass of that one. .25 grams, or the closest we can get to it. 5.29 grams would be the best. Now, the reason that's 5.29 is because we actually used 4.00 and 20.18. Right? And we ratioed these two, which would be a slightly larger number than 5, which would give us a larger value. Right? But the best answer is A. All right. Okay, that was 60. 67. A hydrogen balloon is at 25 degrees C. Okay. And 1 atmosphere pressure. All right. It has a volume of 1 liter. Right. And this balloon has hydrogen in it. Let's see, how many grams of argon gas must be added to the hydrogen balloon to achieve a volume of 3.78 liters at constant temperature and pressure? All right. So what's the initial volume? What's the initial volume of this one? Well, it's 1 liter, right? So if we're going to go from 1 liter to 3.78 liters, we're going from this initial volume to final volume of 3.78 liters. What's the change in volume? Right? It's 2.78 liters is the change in volume. And the change in volume is due to only the addition of argon gas. Okay? So the change is 2.78 liters at this pressure and this volume. We want to know what is the added number. Let's see. Yeah, the added number of moles of argon. Why? Because if we know the number of moles of argon, we can calculate the mass. So that's equal to PV over RT. So pressure is still 1 atmosphere. Volume change is going to be 2.78 liters. 0.088206. And temperature is plus 273 equals 298 K. 298. So that's the number of moles of argon. 2.78, 0.08206. That's 0.1137 moles of argon. Now we can convert that to grams. We just need the molar mass of argon is 3995. Which is equal to 4.54 grams. Okay, that's B. Let's see, we ought to be getting close. 74, we got time. 74. You have a partially filled party balloon with 2 grams of helium gas. You then add 3 grams of hydrogen gas. Assuming constant temperature and pressure, how many times bigger is the party balloon? Comparing before and after the hydrogen gas has been added. Choose the best formula to use to solve this problem. Okay, so let's put what we know up here. The party balloon starts off with 2 grams of helium. Okay, then we're going to add 3 grams of hydrogen. All right. Let's see. Constant temperature and pressure. How many times bigger is the party balloon? So temperature is constant. Pressure is constant. So the volume will change and the number of moles will change. Those are variable. Okay. And V for volume, N for moles, true. M for the mass of the gas. And P equals the pressure of the gas. Well, we're not given variables for the molar mass because that would be required to calculate the number of moles of each. But once you calculate the number of moles of each gas, then you can change the volume. Right? You know the volume before. Then we're going to find the volume after, right? How many times bigger is the party balloon? So if we say this is after and this is before, then the ratio of this one to this one is going to be related to the number of moles of the gas after to before. Okay? That's Avogadro's law. So that seems to satisfy, right? A, temperature doesn't change, so A can't work. Pressure doesn't change, so B can't work. C doesn't work because the relationship of volume to volume is not based on mass, it's based on moles, right? So we can't use C. And E, we can't use E because pressure didn't change, right? So by process of elimination, the only one out of that group that gets even close to answering the question is D. It relates volume to number of moles. That's not a very good question, I don't think. I think it's kind of tricky. 78. Which conditions of pressure, temperature are most ideal for a gas? When we talk about ideal behavior, we're talking about satisfying the conditions of the kinetic molecular theory. So in order for the kinetic molecular theory to operate within normal parameters, in other words, ideal situation, we have to be sure that the particles don't interact, right? They don't attract, they don't repel to a significant extent. So we need to limit the number of collisions. And when you limit the number of collisions, you need low pressure, which is related to low number of moles, of course. And you need the individual particles of the gas must have sufficient energy so that any interactions that may occur are overcome by the power, the force of the collision. So we want to increase the forces of the collision, which means high temperature, high kinetic energy. So that means high temperature. Okay? So low pressure, high temperature will produce an ideal gas. Now, under what conditions do we have those? Low pressure, 1 atmosphere is low pressure, right? As compared to, say, 100 atmospheres. But you can actually go up to maybe 20 or 30 atmospheres and still have ideal behavior. Temperature. What's high temperature? Well, compared to what? Compared to absolute zero? Yeah, 273 degrees K, 273 K is high temperature. That's standard temperature. Room temperature will be 293 K, 20 degrees, right? So where I'm standing now in this room, ideal conditions. 79. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of between 80 and 90% carbon by mass. At 145 degrees C and 1 atmosphere, the density of the compound is 2.45 grams per liter. What's the molar mass of the compound? All right, let's work this problem backwards. If we want to know the molar mass, what does that mean? That's my abbreviation for molar mass, molecular weight, is the mass per mole. Okay. We're given density. What's density? Well, density equals mass per volume. And the compound is 80 to 90% carbon by mass. All right. And we have, we also have this, when we're talking about moles, we have moles here, we have volume here. We also have this equation, right? Because it's a gas, right? We're told it's a gas, a gaseous compound, carbon and hydrogen. Okay, what's the molar mass of the compound? Well, let's see. We're given, right? Let's put up what we're given now. Temperature is 145 C. Temperature equals 145 degrees C plus 273 would be equal to 418 K. We're also told the pressure is 1 atmosphere. Okay. And we're told the density is 2.45. Density equals 2.45 grams per liter. All right. So let's see if we can combine these three equations into one that gives us the molecular weight, and then see if we have the information that will go into the equation and solve it for us. Okay. So if we solve this one for moles, then it will go in here. Like that. So that means, let's go over here. Molecular weight equals, and moles would be PV over RT. How about mass? Well, mass would be like that, and that would be D times V. So mass is D times V. All right, so let's solve, right? The denominator of the denominator is the numerator. So we have D, oops, all right. D times V times R times T over P times V. That goes out, that goes out. And we're still equal to molecular weight. Now, R is a constant. We have temperature, we have density, we have pressure. We can solve this equation, but we got to be sure the units are correct. And so R is in what units? R equals 0.08206 liter atmospheres per mole K, and molecular weight is grams per mole. Okay. So if we put density in here, it has grams and liters. That's good. If we put atmospheres in there, that's good. If we put, well, moles are by themselves and K is temperature. So I think we can put those values directly into this equation. Density equals 2.45 grams per liter times 0.08206 liter atmospheres per mole K. And then temperature is 418 K divided by pressure, which is 1 atmosphere. Okay. So liters, denominator, numerator. Atmospheres, numerator, denominator. grams, keep it, K. So we're going to be left with grams per mole, All right. So the molecular weight, and by the way, this problem says 80 to 90% carbon, doesn't matter. We're going to answer the question without that bit of information. 2.45, 0.08206, 418, and divided by 1. So that's 84.0 grams per mole. That's A. All right. Yeah, just about out of time. We can see how many more problems we have to do. Let's see. All right. Determine the molecular formula for the hydrocarbon. Let's see. 81. Yep. 81. All right. This is our last one, so I'm going to run over time and finish it. 81. A 15-gram sample of hydrocarbon is placed in a balloon at 1 atmosphere and 25 degrees. And the volume of the balloon is 12.2 liters. The hydrocarbon is 79.89% carbon and 20.11% hydrogen by mass. Determine the molecular formula. All right. Remember when we were determining formulas for compounds, we had to go through 2 steps. We had to do the empirical formula, and then we had to convert that into the molecular formula. Right, so we have enough information with the percent composition to do the empirical formula. So let's do that one first. All right, we have hydrogen, and we have, let's do carbon. Let's put carbon on top. Carbon, hydrogen. We have a percentage of 79.89% carbon. And 20.11% hydrogen. Remember, we can't do any calculations with percent. We need mass. So we assume 100-gram sample. Now we have 79.89 grams of carbon and 20.11 grams of hydrogen. Now we can convert them to moles and find the molar ratio. If carbon is going to be, well, 0.01 grams per mole, and hydrogen is 1.01 grams. Okay. So we need to find the ratio. That is 79.89 here, 12.1. And this is 6.652 moles of carbon, 20.11. This is 19.91 moles of hydrogen. Now, how do we get a whole number ratio out of this? Well, first of all, we take the smallest number and divide everything through by that number, because this ratio is fixed now. This is that many moles of carbon, that many moles of hydrogen. So if we do something to one of them, we do the same thing to the other one, we haven't changed the ratio. So 6.652 and 6.652 equals what? That's 1, obviously. And this is 6.652. And this is about 3. right? Rounded off, it's 2.99. So the empirical formula is CH3. And remember, we need to know that multiplier, right? So this empirical mass or empirical weight equals 12.01 and 3.03. So it's 40515 grams per mole. So if we can determine the molar mass of the compound and compare it to that, ratio it to this, we'll find out what that value is right there. So now we have to go to, well, we used 100 grams to do this calculation, but there are actually 15 grams of sample in the balloon. All right, so to determine the actual molar mass, we need mass and the number of moles, mass per moles. Well, we know the mass is 15 grams. We need to know the moles. All right, so do we have enough information? Well, let's see. We have pressure equals 1 atmosphere. How about volume? A volume is 12.2 liters. Temperature equals 25 degrees plus 273, which is 298. Okay. Yes, we can find the moles. Right. So PV equals nRT. That means, let's see. PV equals nRT. N equals PV over RT. PV over RT. Pressure is 1 atmosphere. Volume is 12.2 liters. R is 0.08206. And temperature is 298. And we can find the number of moles. 12.2, 0.08206 divide and 298 divide is 0.499 moles. Okay. So the molar mass or the molecular weight of this compound, we're going to substitute here 0.499 moles. Divided into 15 is 30.07 grams per mole. And we want to find out what N is. Right? N is approximately 30.07 divided by 15.04 equals 2. So that means CH3 with a 2 here equals C2H6. That is our molecular formula. Okay, and that's the end of the review for this chapter. We'll have opportunity to bring problems to me next Thursday. I'll be zoomed in for about a half an hour in case anybody shows up. And if nobody shows up after a half hour, I'm going to shut the thing down. All right, so if you have problems, come at the beginning of class.